This is lecture under chapter 4 in Solid of Mechanics 2, School of Mechanical Engineering, UTM. Is thick cylinder. We have discussed thin cylinder in chapter 1 under stress transformation. Now is thick cylinder. It's based on the notes in e-learning. The learning outcome that we expect everyone to be able to achieve is number one, be able to develop the equation for radial and circumferential stresses in a thick cylinder using Lame's theorem. So there are unique equations for each problem. Able to correctly identify boundary conditions for Lame's equation, and finally able to solve thick cylinder problems using Lame's equation. So the diagram at the bottom here, it shows thick cylinder. On the left is called a closed end thick cylinder. So this is a closed end thick cylinder, and this is called an open end thick cylinder. Okay. Now why is it called closed? Because the cap here, the end caps, are fixed to the cylinder itself. Therefore, the cylinder will move together with the caps. So they are called closed ends thick cylinder. The one on the right, the cylinder and the caps can move independently. That's why it's called open-ended thick cylinder. So the thick cylinder is open-ended. The definition of thick cylinder continues from the definition of thin cylinder. For thin cylinder, we have d over t is greater than 20. So for thick cylinder, d over t is less than 20. And d in this case is still the internal diameter. So for thick cylinder is very significant because the thickness is significant. The assumption that we do or that we use when developing this theorem used by Lame is hoop stress or circumferential stress, depends on which text you use. Some will call circumferential stress, some will call it hoop stress. They are the same. And radial stress, sigma r, is not constant across the thickness of the cylinder wall. Right? In thin cylinder is different. And there is a great stress gradient across the thickness of the cylinder wall. Second assumption, shear stresses are not present in the principal planes. This is the same as stress transformation. When we are on the principal planes, there's no shear stresses. So for cylinder, under pressure only, the circumferential plane, radial plane, and longitudinal planes are the principal planes. The derived theory is applicable to sections remote or far from its ends, as we have discussed in earlier lectures. Why it is important to take sections far from its end. And axial or longitudinal strain is constant. Okay, thick cylinder, open-ended. When it's open-ended, the cylinder moves independently of the cap. So when it's open-ended, sigma L is 0. And when sigma L is 0, we have a plane stress condition. Okay, so we have 2D principal stresses, which is sigma hoop or sigma C. This is sigma C or sigma hoop. Okay, and sigma R. Sigma L is 0. So this one now becomes 0 for our first condition, open-ended. For second, closed ends, sigma L is not 0. So we have a 3D stress system. And it is possible to be plane strain, possible, not always, if the ends are fixed. So you have a cylinder, for example, right? So you have a thick cylinder and you have the ends here, they are fixed. And the ends here are fixed as well. Okay? So meaning there's no strain in the longitudinal direction. So if that's the cylinder there, if there is a cylinder and P is inside PI and PO, so it cannot expand longitudinally. So strain L and sigma L is not, sigma L is not 0, strain L is 0. So in that case, it's plane strain, but only in this case. So we go to Lame's theorem. Lame's theorem is based on taking an element of the stick cylinder out, right? So in the circumferential or hoop direction, we have sigma C or sigma H. Okay. And in the longitudinal direction, we have sigma L. And in the radial direction, we have sigma R, right? So if you take a small element from the wall of the thick cylinder, this is the stress condition that we have. And the forces that they generate are in equilibrium, right? So this is circumferential or hoop, right? So we have three stresses which are mutually perpendicular to each other when the angle is very small and the stress element is very small. Now sigma C is almost perpendicular to each of the other stresses, right? And so the corresponding strain, remember our Hooke's law, we have strain is equal to 1 over E sigma L when the strain L, and then the other two are perpendicular to the longitudinal direction. Similarly, strain C, circumferential or hoop, is equal to 1 over E times sigma C minus nu of the other two stresses. So we have three equations here, which we can solve simultaneously. Okay. But what we are interested in is equilibrium of forces, right? So when we take equilibrium of forces, so sigma C, they have a small angle, very small angle, depending on whatever subtended angle that we take. Now let's say we take del theta. Therefore, the angle for each side will be del theta over 2, right? So if we take out, we have sigma C, that is sigma C, and it has two components. A vertical component which is sigma C sine del theta over 2, and a horizontal component which is sigma C cos del theta over 2. Okay, so let's take a look at balance of forces. If we assume the length to be 1 meter and the thickness to be 1 unit, so we have a force, right? When we have stress times the area. And over here, that's the stress times the unit area. Now, the length of this arc here from mathematics, if this is R until this point, that's internal radius, right? Or you might use a small letter R. If there is the internal radius, therefore the length of the arc is R del theta for this portion here. So that is r del theta, that length. Whereas the length outside here is r plus del r, because that's the thickness, right? Times del theta. Okay? And the area then is equal to this times 1, because we assume the length is 1 meter. Okay? Assuming 1 meter length of the stress element. Okay, the area on the bottom surface is r del theta times 1. Now, if we take equilibrium of forces in the vertical direction, so that we can solve the relationship for sigma r. So we have vertical force upwards is sigma r plus del sigma r times the area r plus del r del theta. Okay, so this is the area, that is area of top surface. And downwards we have, first, this is sigma r acting on the bottom surface, and the area of the bottom surface is this. Okay, so this is area of bottom surface, right? Plus, we have vertical component of this one, sigma c on the right and sigma c on the left. So we have vertical forces, the component of sigma c, and there's two of them, one on the right and one on the left. So we have 2 times sigma c times the area, right, which is del r times 1, because the thickness is del r, and sine del theta over 2. That is the downwards component. So when we balance the forces, we have sigma r plus del sigma r times r plus dr times del theta, d theta, because for very small angle, sine of the angle is equal to the angle itself, provided the angle is in radians. So we can omit the sine in both sides. So I left with this equation on top here, which then we can resolve to get this equation. Okay, we have sigma c on the right and sigma r on the left. So you can delete them. Okay, and within limits, we have d sigma r over dr is equal to sigma c minus sigma r. So that is our first equation for relationship between sigma c and sigma r. Now, it can be shown that the longitudinal stress and strain are the same at all radii, right? But if you want to find the details, you can go online and find the information online. Okay, the longitudinal strain is given by the Hooke's law equation from previous. And since strain L and sigma L are constant across the thickness, then it follows that sigma R plus sigma C are constants. Okay? If strain L is constant, if this is constant across the thickness, then this is also constant. And when that's constant, then this is also constant, right? Sigma C plus sigma R. Sorry, there's a typo in the text there. It should be sigma r. Something goes missing there, half. Okay, the solution is then simplified to say sigma r plus sigma c is a constant. We just put the constant as 2a. Now there's a mathematical reason for doing that. You will see that later on that's more important rather than putting just a there. So we have sigma c is equal to 2a minus sigma r, which we can then solve together with equation 4.1, right? Putting 4.2 into 4.1, we have then this equation here. So the rest are just mathematical solution, which you can go through. And finally, we have this equation here. And we can then integrate both sides. If you take dr to the right, so we have 2 sigma r dr, and on the left is dr squared sigma r, or sigma r dr squared. Okay, so if we integrate this with respect to r, then what we have is r squared sigma r is equal to integral of 2 sigma r dr, and what we then have is ar square minus another constant b, and b is the constant of integration. So we have this equation here, which is equal to r squared sigma r is equal to ar square minus b. Now if we rearrange this, we'll have this equation here. Sigma r is equal to a minus b over r squared. Now this comes from this equation here. Okay, so that is our first equation. And if we replace sigma r into our initial equation of sigma c minus sigma r, right? Because we have sigma r plus sigma c is equal to 2a. Remember this equation from previous page. And we replace sigma r is equal to a minus b over r square here in the equation. Then we get sigma c is equal to a plus b over r square. So we have two equations here. One is for radial stress equation, and the other one is for circumferential stress equation. So these two equations are called Lame's equation. We will use this equation to solve thick cylinder problems. Okay. In order to use this equation, remember A and B are constants. So for a certain location, on a specific thick cylinder, we have a specific value for A and B, which we have to find. We have two equations, we have two unknowns. So to find A and B first, then only we can solve for sigma C and sigma R, or whatever stresses you want to find. Then we need to know certain boundary conditions. The boundary conditions will help us determine A and B. So what is a boundary condition? It is a known answer. The boundary condition is a known answer or value. What are the values? It can be sigma R, it can be sigma C, right? So what is sigma R? Now, if you look at the thick cylinder, on the outer surface and on the inner surface, this is inside. So we have Pi, this is outside, so we have Po. And what are pressure? Pressure acts perpendicular to the surface, right? Pressure acts perpendicular to the surface. In other words, in the material itself, inside, so if we take a stress element there, so remember our sigma r is like that, is going out, but the stress from the pressure is going in, therefore this is equal to negative of the pressure. So if you take a stress element inside, then the radial stress sigma r is minus pi, right? Is compression. So there is if we can find these two, then we have two equations for sigma r, which then we can solve to find a and b because they have different radii. Okay, the radius for the internal is ri, the radius for the outer surface is ro. So we have ri here and we have ro over there. Sorry, ro, right? So we have two radii. The other thing that we might know is sigma circumferential. Now that depends on the material properties or whatever condition we have put the thick cylinder into a certain stress. Okay, so it says here when atmospheric pressure acts on one side of the wall, it is best to use gauge pressure similar to thin cylinder. So we are using gauge pressure so that we can eliminate atmospheric pressure. So if you use gauge pressure for Pi, then if outside is atmospheric, this is equal to 0 if it is P atmosphere. Right. Boundary conditions, as I mentioned before, we have two earlier due to atmospheric pressure and internal pressure. Right. So that is in this paragraph here. So knowing those two, then we can solve for A and B. So if you have a closed end, outside is all PO and inside are all PI. And again, P will create the radial stress. Now, when we have internal pressure and outside is atmospheric, okay? Now, the stress element generally is shown here. That is the general stress element. So if we plot distribution of sigma r and sigma c, or this is sigma c, okay, or sigma h, or sigma h. Now if we plot them, when internal pressure is applied and outside is P atmosphere, which is equal to 0 P gauge, right? Therefore, on the outer surface, the radial stress is 0 and it reaches the internal pressure Pi on the internal surface. And we have a distribution which is x squared, right? Remember the equation is sigma r is equal to a minus b over r squared. So it depends on r. And for sigma circumferential or sigma hoop, we also have a curve and is not equal to 0 on the outside because we do still have some value of circumferential stress or hoop stress on the outside surface, and it is highest on the internal surface, and it is much higher than Pi, right? So the circumferential or hoop stress is the largest stress in a thick cylinder, and when you have internal pressure only is the largest on the internal surface. This is an example. I'm going to go through halfway and you will continue the rest of the way. because the rest is just mathematics. And we'll discuss that in the next lecture or in the online lecture. Now, this example says we have a hydraulic cylinder. You know what is a hydraulic cylinder? The one you can find on cranes, on what do you call, bulldozers and backhoes, or all those machine tractors. You have this cylinder that can be used to push components up and down. Okay, so you might have uh, a crane or a dozer now, or a truck even. You can find trucks where we have, okay, where we have this cylinder pushing the back part out. So we have, this is called the hydraulic cylinder or hydraulic ram. So we are talking about this part here because there's hydraulics in there. Now the other part is normally solid bar. So it says the cylinder has a 100 millimeters internal diameter and 140 millimeters external diameter. So now they give you DI and DO, right? So you have DI 100 and DO is 140. Now it says is pressurized internally. Pressurized internally. So this is PI, right? 100 megapascal gauge. Determine the radial and circumferential stress at the inner and outer surfaces. These are the values given to you. E is 205 gigapascal. Poisson's ratio is 0.25 if you need to use them, right? So first, we have our general equation for Lame. So we have sigma R is equal to A minus B over R squared. Sigma C or sigma H is A plus B over R squared. Now these two are our general equation for Lame, right? For thick cylinder. So R is given. Internal diameter is 100, so internal radius is 50. Okay, and outer radius is 70. Pressure wise, internally we have internal pressure of 100 megapascal, and on the outer surface is atmospheric, so it's 0 megapascal gauge. Both are compressive, okay, because the stresses are due to pressure. If we substitute these values here, these two values into Lame's equation, now we have only sigma R, but we have two values of sigma R at two locations, R50 and R70. So we use the equation for sigma R twice. So first we have sigma R is equal to A minus B over R squared, where R is 0.05, will give us minus 100 megapascal when A is 0.05. When A is 0.07, the pressure is 0, so sigma R is 0. Solve simultaneously these two equations. We'll get B is 510 kilonewtons and A is 104 megapascal. Now, if you look closely, you can see that A must have the same unit as sigma R, whereas B is equal to sigma R times R, right? So if this is meganewton or kilonewton or whatever unit you have, Newton per meter square, and R is meter, right? R is meter. So you can cancel out and you have newtons. Sorry, meter squared because that's r squared. So we are left with Newton. Okay, so we cancel out both sides. And once we have A and B, and we already solved the first part of the question, which is radial stresses at the inner outer surface is already given from the pressure. So we know sigma r is minus 100 and 0. So we are left to find only the circumferential stress on the internal surface, all right, and the outer radius. So we apply A and B into the equations here. So A is 104 megapascal, B is 510 kilonewtons. You apply in this equation, remember to use the same units. Then we'll find that when we have R is 0.05, sigma C is 308. When R is 0.07, sigma C is 208 megapascal. So how we get this answer, that's up to you to do as your exercise, right? Thank you. I see you in the next lecture.